In the past two lectures, we examined the commutator, which was the product of operators subtracting their multiplication in different orders. And we saw that was tied to the fact of whether there can exist sharp values for the observables or not. And what we want to talk about here are two incompatible observables, meaning the commutator is not equal to 0. And we want to examine the implication of that. We'll get to that in a moment. We also examined in the previous lecture how to calculate expectation values for our observables in a particular state. And we want to look at the statistics and here and see if we can get a connection between the statistics that are observed and the commutator essentially. So first of all, let's consider an eigenstate of some observable A, and we'll call it A2 just as a random value, which means that if we act on A with A2, we get the A2 value out multiplied by the state vector. And we want to find the expectation value and the variance for this object. So the expectation value we went through previously, and we see that we get, this is how we calculated. This is the classical, normal, probabilistic way of calculating it, of course. We sum over the product of the outcome value times the probability that the random variable, or operator in this case, is equal to that value. Now in this case, if it is an eigenstate, that means it's not in any other state, which means that the probabilities here, the only one is when it's A2, because it definitely has a value A2, and any other eigenvalue of A, the probability is 0. So this probability is 1, and we simply get A2. And we're putting this subscript here. We'll change this notation back and forth a little bit, just to emphasize that the expectation value is dependent on which state you're referring to. Now let's calculate the variance. Recall the variance from the discussion of probability. You can express it as follows, as the expectation value of the random variable squared, or we'll just talk about operators now, minus the square of the expectation value of the operator, again in some state here, A2. Well, again, writing this out classically just like we do, again, we can express this in terms of our Brockett-Born rule if we like, but let's just keep it like this. But again, we have the square of the value times the probability for that value, and then the expectation with that square. Okay, that's just the definition. Now, it should be obvious here that this vanishes. Because again, the probability, the only one that's non-zero is when it's A2, so we get A2 squared out from this term, and this one, as we found before, is A2, and we square that, we get 0. Now, this should be obvious from the definition of the variance, where if you recall, the definition of the variance, if we have, so let me just kind of say we have some distribution, even though we're talking about discrete, say we have some distribution here, and we have some mean value, which is our expectation value, if you will. The variance essentially measures how wide or how far does the results fall from the mean. I'll put, and again, variance value, we'll just call it like that. So again, here, because it's in an eigenstate, the mean value is A2. And there's no splay about it, or there's no variation from that because it definitely has that. So again, if you had many copies of the state and you repeatedly measured, everyone would come out to A2, no value would be different than A2, so the variance is 0. There's no variance about the mean. Okay, now let's go and consider an object that has, it's an eigenstate of two distinct observables now. So we're going to call it, for A and B, so we'll call it A2 and B4. Again, those are just random numbers we're drawing here of some eigenvalue. So that just means that when A acts on this state vector, we get A2 times the same vector out. But if B acts on it, we get B4, because that's its eigenvalue. And I'm going to just state it without proof, because it should be obvious if we go through the previous discussion, that both the variances are 0. Variance A and variance B in this particular state is 0. Now, really what we'll often relate this to is not necessarily the variance per se, but really the standard deviation. Or in quantum mechanics parlance, the uncertainty. It's just the standard deviation. And it's just the square root of the variance. It's just a definition. And again, here we just see that, well, if the variances vanish, well, then the uncertainties vanish. And again, to emphasize, the uncertainty is state dependent, so sometimes, just to emphasize, we'll put a subscript here of the state, but we won't always do that. Now, here's the point. So we say here that if this state is an eigenstate of both of these observables, we see that both of the uncertainties are 0, obviously. But, and we said earlier with the commutator, well, that means that the commutator of AB vanishes. That's what we heard in the earlier lecture. But if the commutator doesn't vanish, then A and B are incompatible. And then what happens is that, well, the variances are not necessarily, or they're not, actually both 0. So, for example, what we're going to assume here is that, let's assume that the state is an eigenstate of one of the observables, and we'll say it's A. That means that delta A is equal to 0, the uncertainty A is 0. But if that's the case, we want to go through and kind of show in a simplistic way that the variance B and the uncertainty B is not 0. So this is not a completely general statement. For a general state, we would have possibly the uncertainty in A and B both not being equal to 0. We'll come back to that, and we're not going to do a full rigorous analysis of this. But we do want to kind of go through here and prove this assertion that if A is an eigenstate and the variance is 0, or the uncertainty is 0, then B, it's not 0. So let's go through this, take a few lines. All right, so we're going to take some state now. That's an eigenstate of A, and again, just the eigenvalue A. And again, like we said, here I'm emphasizing this is in the state A. It vanishes, we said that already. But we're going to take now that there's another operator B that does not commute with A. So in that case, what we have is the B acting on the A returns some value B as an arbitrary, but a different vector phi. Now it's important to note, very important to note, that phi cannot be in the same direction or anti-direction as A. It can't be parallel or anti-parallel to A, because then it would be an eigenvalue of A. But it's not. That's the we're showing here. And that's what we said earlier with the commutator. So we want to go through and show that the uncertainty of B is not 0, or the variance. To do that, we need to break this into two possibilities. So we're going to call it possibility 1, that this state that B transforms A into is along the direction of, or is perpendicular to the vector A. It's in the subspace that's perpendicular to A. And note, depending upon that, that may be an eigenvalue of A. The other case is we want to say, well, it's not in the perpendicular direction of A. And that's just we just want to treat these separately to be careful here. Okay, so let's calculate the variance of B. So in the first case, where it's the perpendicular, we can write this out, variance of B. It's going to be A here. This is the definition. But B acting on A is going to be proportional. We'll call it B here, A perpendicular. So the first term, we're going to A, B, A perpendicular here, multiplied by B. And the second one, A perpendicular. But these vanish because they're perpendicular. They're orthogonal, so they vanish. So the second term vanishes, and the first case is simply A, B acting on A perpendicular now. That's because it's squared. And let's define this to be the following. Some other vector psi, and some other random, well, it's determined, but we're just putting a coefficient there, c. So what we're doing is we're defining that B on A perpendicular is equal to c psi. Now, it should be the case that psi is not along the direction of A perpendicular, because that would mean that's an eigenstate of B. And we can do a more formal proof and take care of all possibilities there, but we're going to leave it at that now. But it's not going to be just because of the fact that it would be an eigenvector. And if that's the case, then this inner product doesn't vanish, A on psi, because it's not perpendicular to it. It's not in the space of that, and thus the variance does not vanish. Okay, second case. Well, again, the key thing here, the uncertainty in A is 0, the uncertainty in B is not 0 in that case. For 2, again, we do the same thing. I'm going to use a different letter here, D, to indicate the action of B on it, where now these don't necessarily vanish. So it's A on psi. But we need to note here that b on psi is not parallel to psi. Otherwise, it can't be that BA is proportional to psi. Now, phi, excuse me. Now, we could go through a proof here to show this, and it might be worthwhile just to make sure that we're rigorous here. So maybe I might take a moment just to do this. But again, let's make the assumptions that we have here, that B on A is equal to D phi. And now we'll just say, we'll make the assumption that B on phi is equal to, I'll call it C of phi. And we want to see, well, is that the case? Is that possible? Well, all we have to do is consider, well, there will be an inverse operator for B. There will exist an inverse such that B inverse, that's going to equal to the identity operator. So that when that acts on A, B minus B, we have to get A back because it's the identity operator. It doesn't do anything. But notice what that does. This tells us that B minus the inverse acting on phi has to equal 1 over D A. Because that's the only way we can get back to where we were. Now, if that's the case, let's look at this the identity B minus 1B acting on phi now. And we'll make the assumption up here that it's equal to C phi. So we'll say that this is B minus 1, and we'll put a factor out the C, phi, like that. But, I think I had a D missing here, D, so this should be a D there. Did I do it? Yes. But again, acting now, we know we said that the operation just above, that B minus on phi, has to equal 1 over D on A, which gives us 1 over D C A. But notice that the only way this can be true in any way is as if psi is equal to, because we're not getting the same thing back. It has to equal phi. So the only way this would be true is if phi is parallel to A, which is not the case because that would be an eigenvector. So this just proves that these are not parallel. That's all. Not critically important, but we just want to make sure we're thorough here. All right. So that means that we want to define B phi on some psi, where again, psi now, like I said, is not along phi. It has to change into something else. And it can't change back into A either. If that's the case, then, and we go through and calculate the variance, we get now that dA on psi minus d squared A phi is not equal to 0. Now, you might not buy that. You might want to spend a little effort here, but it should be clear that these are not going to give the same value. We won't go through that proof. You can prove that yourself, but it's not that hard. But again, the point is the variance or the uncertainty in B is not 0 if the uncertainty in A is 0. And the two operators do not commute. Now, the important thing is that it's the commutation relation that's the source of the uncertainty in these complementary observables. Now, there is a relation which we're not going to prove here. It would push us a little bit too far into dealing with operators in the state vectors, but showing how the uncertainty arises from the commutator, essentially. And that's called the generalized uncertainty principle. And it looks as follows, that the product of the uncertainties in the state psi, I'm emphasizing here that these are calculated in the state psi, that product is greater than or equal to 1/2 the commutator but acted on with that state psi, and also this modulus. So really this would be the modulus square of this, but then we're taking the square root in the end. So you can think of this sort of as an absolute value. Any value of I will come out. Will be 1, I should say. Yeah, so again, let me just emphasize that just for absolute clarity. That second term is going to be 1/2 the square root of, I'm going to shorthand it like that. Square like that. So we're taking the modulus square, then taking the square root. So again, so if the commutator is proportional I, there will be no I in the end. That's all. We don't expect our variances to be complex. Now, for proof, we'll refer to the Susskind quantum mechanics lectures 5.3 through 5.7, where he goes through and shows the various steps in proving that. It's worthwhile, but I wouldn't. It's not going to be. We don't want to emphasize it too much in this course, but we do want to. If you're curious, you can look there. Now, you may have heard of the uncertainty principle before. I'm assuming you have, and specifically, you've probably heard of what's called the Heisenberg uncertainty principle, which this is definitely related. And the Heisenberg uncertainty principle is usually related to the position and momentum observables. Now, we haven't introduced the position and momentum observables yet, and we will in a later lecture. However, we're just going to state the result here so that you can just make the connection here. But one of the challenges is that because position and momentum are continuous observables, that means there's an infinite number of outcomes, and the Hilbert space then is infinite dimensional. So things get, it's a little different, but it is essentially the same mathematical formalism. In this case, since we're dealing with continuous outcomes, it turns out our operators are going to be differential operators, or there can be differential operators. So let me just show the result. So we're doing what's called the x bases, where x takes the simple form x, the variable x, and the momentum operator is minus IH bar partial x. It's a derivative operator. Now remember, just as before, our operators don't have a meaning in and of themselves. They always need to act on a state. Now for these cases, the state we're going to refer, we can talk about it in terms of kets, but actually the way we will do it is in terms of a function of the position. And that's why we're in the position bases. So what that does, when we work out the commutator, acting on some state, psi, it looks like this. So we have our commutator acting on psi. Now again, we do this to emphasize that if you're going to do calculations with your commutator, it's always, especially in this continuum formalism, it's always important to multiply by some function. You don't make an assumption on it, but you can just say some state vector there, or state function, wave function we call it. Now, carrying this out, I factor out the minus IH bar from P, which is in both terms. And we notice that we have XP is the first one, so x times partial x, and we subtract the inverse, partial x, and then all that acting on psi. Now, this is why we got to be careful because, well, the first term is pretty simple to do, but here we have to do the chain rule because it's the partial derivative of x on the function x times psi. So again, the first term, I'm going to use a prime notation just to keep things simple. That just means derivative with respect to x, partial derivative with respect to x. So this just acts on psi, so we get x psi prime x. The second term we have to do twice, the chain rule. So we have to derivative of x with respect to x times psi, that just gives us psi x in the end, and minus that. And then we have to take, there's a sign error here, I think. Then we have to take x times the derivative of psi prime, just here. There's supposed to be a minus sign here. There. But notice when we do that, the first and last terms cancel. So we end up with IH bar psi. So the commutator is just IH bar 1. Then that's usually just see IH bar. It's implicit that there's a unity operator there because it is an operator. Well, now if we take that and we just insert it into this, well, we just put an IH bar here. And again, remember that we're taking the modulus square root, so the I goes away. So then we just get H bar over 2. And this is the Heisenberg uncertainty principle for position and momentum, as you often see if you've read anything on quantum mechanics. And again, it's saying that the product of the uncertainty in x times the product times the uncertainty in momentum has to be greater than h bar over 2. So if 1 is 0, in this case, this is a little different. If 1 is 0, then it has to be infinite uncertainty, and vice versa. But there's a lower bandwidth it can be. Now, in the discrete case, we can get these cases where we can be, we can get one of these to vanish and the other one's finite, but let's not worry about that. And we may come back to, if we have time, to discuss this version of the uncertainty relation later.